Hi. So we are starting our class. So the topic which is going on right now is the rates of the reactions. Rates of reaction. So here some mathematics is involved. So that's why I'm teaching you on the whiteboard. I show you the presentation after this. So till now you have done the meaning of the rates. So what is the meaning of the rate? It is the change in concentration over time. Delta A over, now let's say the reaction is A to B. And then this is how we are writing the rate, which is called as average rate of the reaction. Change in concentration of A. Negative means it is decreasing with time. That's the meaning of the rate. Then we did the rate law. That rate equals to, for this reaction, let's say, is equal to K times concentration of A. It is always in terms of the reactant, always, never in terms of the product, raised to power X. X is the order of the reaction. This order can be 0, 1, 2. Very good, Anil. What is K here? K is the rate constant. Rate constant. Now, this is one definition of rate. This is the rate law. So if I replace this rate by this equation, then it becomes minus delta E over delta T, which is equal to K times concentration of A raised to power X. X can be 0, 1, 2. K is the rate constant, yes. Zero order, first order, second order. We did the units also, units of K. So in the last class, we practiced some questions based on rate law. Today, we are going to do integrated rate laws. Integrated. Rate laws. This is calculus. So AP is not asking any mathematics about it, but they are very important to understand the kinetics of the reaction. So I will give you very brief mathematical background about it, and I show you some thing to make you understand what we are doing. The aim is only to make you happy that, okay, it means this. Otherwise, AP is not asking any mathematics about it. So what is the meaning of integrated? You know, children, this expression is called as differential. Delta means change, change. This is differential. Integrated means you have to integrate this. You have to integrate from 0 to time t. So all the differential like dx over dt, when you integrate this of dx, then it becomes x. dt will become t, like this. So there are some integration rules, calculus rules, which you have to, you can understand when you are going to do calculus. If you are already doing, maybe you are aware of it. Okay. So let's do the integrated rate laws. This one is the simple average rate law. This one is average. And this one is, now we are going to do integrated. And what is this one? Differential rate law. Average, differential. Now we are going to do integrated rate laws. Okay, let's start with zero order. Ready for zero order? Zero order reaction. So let's say the reaction is A giving you B, the product. Now the rate law, rate equals to, for zero order, K times concentration of A raised to power 0. This is the zero order, which is nothing but rate equals to k. Anything raised to power 0 is 1. So rate equals to k. But what is rate for this? Rate is minus delta A over delta T. Change in concentration of the reactant over time taken. We are okay with this? Now I'm going to replace this R by this equation. Minus delta A over delta T is K. Now you need to integrate this equation. Integrate. Integrate means how the mathematically how to represent over a change from 0 to T. 0 means when the time is 0 initial, and T when after 10 seconds, 20 seconds, 30 seconds, like this, 30 minutes, whatever time they are talking about in whatever units. Okay, so I'm going to integrate this equation from 0 to T. I will rearrange the equation like this. Minus delta A is K delta T. I'll take this minus on the other side like this. I'll integrate. K is a constant, so it will be out of the integration, 0 to T. Now what is this? This will become, you know what this will become? It's delta difference from 0 to T. This will become A T final minus concentration of A at time 0. See, this is the difference. The concentration of A at time T, T is any time during the experiment. And this is concentration of A at time 0 when you just started. This is initial. You just started. And what will become to this? Minus K. This delta T is T minus 0. No one is asking this mathematics. It's just for your, what you can say, for your satisfaction, I'm doing it. Otherwise, no one is asking. I can avoid it, but it's okay. We should know how. And this is minus KT. This is your integrated rate law for zero order kinetics. It will be given to you in the exam. In the formula sheet, it will be there. What is AT? This is the concentration of the reactant at any time T. A is the reactant. See here, this is the reaction. The reaction which we are talking about is this one. A is the reactant. This is the concentration of A at any time T during the experiment. Minus concentration of A when you just started the experiment initially, when the time is 0, is minus K is the rate constant, T is the time. So you can rearrange this equation. AT is minus KT plus A naught, right? I can rearrange like this. But what is this equation? Don't you think it represents a straight line? It represents a straight line. So when you draw a graph of y and x-axis, what is y-axis here? This is y, concentration of AT. What is x? This is x, see? This is time, time is x, t. I hope you can compare this, straight line equations, this one. So I'm comparing my equation with straight line equation to check my coordinates. Y is this, X is t. And what is B? B is when the time is 0, whatever initial concentration, we call it as y-intercept. That is your initial concentration, A naught, initial, when the time just started the experiment. When you draw the line, you'll get a straight line like this. Negative, why? Because the slope is negative. What is m here? Minus k. Very important question. Zero order kinetics, the average rate law is this, average rate is this. The rate law is this. Generally, we call it as differential. But when you integrate, it mathematically changes its form like this. This mathematics, just ignore it. Not needed. If you are good in mathematics, you want to do it, do it. If you are doing calculation, otherwise no one is asking. This equation will be given to you. If this equation is written, then it means they are talking about zero order kinetics. This is zero order. You need to identify it, that it represents zero order, which can be rearranged like this. This represents a straight line equation. A straight line equation means you can compare the coordinates. You know what is there on the y-axis, what is there on the x-axis. When you draw a graph, you get a straight line with negative slope, and slope of the line is rate constant. Okay. So for a zero order kinetics, concentration of A at any time t during the experiment versus t is a straight line. This is a straight line. Is it okay? We are good with this? Okay, that's the integrated rate law for zero order kinetics. Exactly same thing I will follow for first order and second order. Exactly same story. I will give you the differential rate law, then I'll integrate it. I show you some mathematics which is not needed for your learning, but we can do it. And then I'll convert that equation into a straight line equation. Then I'll make a graph. And then one more thing we are going to do, calculation of half-life of a reaction. Half-life of like zero order. So let's try to understand the half-life of zero order. What is the meaning of half-life? Any one of you know it? Meaning of half-life? Half-life means if you started with this concentration of A naught, when this concentration becomes exactly half of its initial, the time taken, so please understand the meaning of half-life. The time needed to decrease the initial concentration to exactly half of it. Whatever time taken, that is the half-life of the reaction. See, Anil is also writing the same thing. So if I started with A naught and the concentration left is now exactly half of that, then whatever time is taken, that is called as half-life of the reaction. Okay. Now, what is the half-life of zero order? Let's see. I started with A naught, and now the concentration when the after first half-life means I can write it like T over 2 like this. T is half-life, right? Is equal to A naught over 2. Okay, let's make it simple. Means the concentration of A left after half-life, after T is the half-life here, is A naught over 2. Is this mathematics clear, children? This one? To all of you? Okay, good, Azuni. Now what you have to do, you have to plug in this value in this equation. You can do it in this equation. What is 80? What is 80? I'm plugging this in this equation, children. Here. I'm plugging 80 as A naught over 2 and minus A naught is minus K. What is T? Half-life. T is half-life, right? So I'm writing T 1 by 2 as a subscript to represent half-life. So half-life is represented by this symbol, right? Rearrange. Check how much is this? Isn't it A naught over 2 minus is minus K T half. So what is T half, children? T half is A naught over 2K, isn't it? There is no space here, so I'm writing here. T half is A naught over 2K. This is the half-life of zero order kinetics. Everything, whatever I'm doing here is for zero order kinetics. So I discussed with you the average rate law, the differential rate law, the normal rate law, then integrated, then we derive this integrated rate law for zero order, rearranged it, made the graph for zero order. Everything is for zero order. So A concentration of A versus time is a straight line for zero order. Then half-life of zero order. And we found the half-life of zero order is A naught over 2K. Very simple question. All ears here, please understand the question and try to answer. If T half, we are going to discuss T half, the half-life. If the concentration, initial concentration is more, what happens to T half? What happens to T half? If the initial concentration is more, T half is more or less? Look at the mathematical equation. Very simple question. It's more. Understand this. So is this half-life of zero order kinetics constant? No, it changes. It depends on initial concentration every time. You start with 20, you start with 10, you start with 5, you start with 1 molar. Half-life will be different. So as the initial concentration changes, half-life changes. Initial concentration is more, half-life is more. Initial concentration is less, half-life is less. Are we okay with this, children? This one? From this equation? Generally, AP chemistry is not so much into half-life of zero order and second order, but it is too much in the half-life of first order. You will understand why. So half-life is the time taken to decrease the initial concentration to its half. Then you can say that at the half-life, the concentration of A left is exactly half of the initial concentration. Plug in this value in this integrated rate law, rearrange everything, and you will get the mathematical equation for the half-life of zero order kinetics. Taking you now on the next whiteboard. Going on the next whiteboard, children. Same story I'm going to repeat. Same. But this time for first order kinetics. First order kinetics, right? So reaction is A to B. What's the rate? Average rate minus delta A over delta T. What's the rate law? Rate law. K times concentration of A raised to power 1. Can I write like this, children? Now we are going to integrate it. This is differential. This one. This is the rate law for first order. Remember? Okay, now we are going to integrate it. Minus delta A is K concentration of A delta T. We are integrating 0 to T. Bring this concentration of A here because A is here. So mathematically, I'm going to take care of this minus also. I'll make it plus. If I make it plus, then this is minus plus delta A over delta T integrate 0 to T is, I'm not asking much questions here. You can understand because this is, I'm just giving you something extra. So 0 to T, there is minus here. When you integrate this, oh sorry, this is A. Sorry, this A, right? Delta T we have already taken on this side. So when you integrate this, integration of 1 dx over x is ln x. These are calculus rules. If I integrate this, I will get ln of this concentration of A at time t, this t, final t, minus ln concentration of A at time 0, initial, is minus k, delta t is t minus 0, so minus kt. This is the integrated rate law. This will be given to you in the exam. You have to identify with which particular rate law is this, 0, first, second, like this. This is integrated rate law for first order kinetics. First order kinetics, right? Rearrange. Rearrange this equation. ln at is minus kt plus ln a naught. Write like this. This equation represents a straight line. Y is mx plus b. Tell me the coordinates of the graph. What should I take here? And what should I take here? Look at this equation, straight line. Ariba, Naisha, Azuni. Yes, what should I take here on this? Azuni is saying you take 80. Why 80? This is why, Azuni. I'm not going to take concentration of A at time t. I'm going to take natural log of concentration of A, right? And on this side, I'm going to take time this x. See, this is how we compare. How the line will go? Check the slope. Slope is negative or positive? Negative. So line will go like this, right? And what is this A naught? ln A naught, not A naught. ln natural logarithm of concentration of A when the time is 0. What is this? The y-intercept here when the time is 0. These graphs are very important, children. It's a major part of your Unit 5 test. You should know everything. Naisha, what is the slope of the line? Slope of the line will give you minus k. Very good, Anil. Like this. That's the integrated first order kinetics. What was the zero order? There is no ln. That's it. Can you see there is no ln here? But here there is ln. Easy to memorize. But you know, children, this equation, this one, the one which I have written here, this one, which is you are saying integrated rate law for first order. It has a different format mathematically, which I have done with you in 0 units. This is ln, what is ln x minus ln y. You know that is ln x over y. You know this? So you can write it like this. So I'm writing it like this. There are different ways which you can use here mathematically. You can say ln at over a naught is minus kt. You can write like this. You know, children, now you can take inverse of this ln. You can take exponential. Inverse of ln is exponential. E times ln is 1. So this same equation, when I take the exponential of the whole equation, then I'm getting this equation. Or a naught e raised to power minus kt. These are different mathematical form. Even this can be written like this. This one. I can get rid of this negative. So when you get rid of this negative, then this becomes negative, this becomes positive. The equation, this ratio will get reversed. A naught over AT is KT. What is K here? What is K, children? Can you type it? What is K? K is a, yes. What is T? T is the, only Anil is answering. What about rest of you? Not understanding? Please keep asking your questions related to what I'm teaching on the whiteboard. Anything. Okay. First order kinetics. This is the rate law. This one. Okay. I'm repeating the story. This is the reaction. This is the rate law. This is the average rate law. You can hear me, right? I'm getting some messages here that my internet is not working properly. Can you hear me, children, properly? Okay, good. So reaction, rate law, average rate law. Now you're integrating. This is the mathematics, which we are not going to learn. But after doing this mathematics, I'm getting this integrated rate law, this one, which can be rearranged like this, like this, like this, like this, mathematical form. And it can be rearranged like this, which is a straight line equation. From there, I made the graph. And here, the y-axis is ln. ln means natural logarithm of concentration of A, natural logarithm. And x-axis is time. And it's a negative slope, straight line with a negative slope. Slope of the line is rate constant, negative k. That's the complete story of the integrated rate law of the first order. Okay. So I can say ln, okay, I have to change the pen now. I can say ln at versus t. It's a straight line. For which order? For first order. First order, right? First order kinetics. First order. We are good? Okay. Now, children, as I said, half-life of the first order is very important. So I'm taking you now on the next whiteboard and I'll talk about the half-life of the first order. Half-life. So what's the meaning of half-life? The meaning is the concentration of the reactant. Reaction is still the same, A to B. A is the reactant. The concentration of A reactant at the time, at the half-life is equal to A naught over 2. A naught is the initial. Yes, Aditi, good. A naught over 2. Now, what is the integrated rate law? ln At minus ln A naught is minus Kt. That was the integrated rate law. Plug in the values. In place of At, write down ln A naught over 2 minus ln A naught is minus Kt. Mathematically, you know that ln x minus ln y is x over y. You know this. But before that, you can get rid of this minus. Put minus here. Means multiply the whole equation by minus. So this will become minus. This will become plus, right? And this will become plus. Is it okay? I multiply the whole equation by minus. This is mathematics, children. Now, I can use this logarithm rule. This minus will go in the denominator and this will be in the numerator. So it is ln A naught, this value, this one, divided by A naught over 2. Can I say that, children? See this one. A naught cancelled. And this is 1 over 2. You know this mathematics? This 2 will jump and come in the numerator. So this becomes, this is actually Kt. So what is this? This is ln2. ln2 is Kt. But this T is T half now. We are working with half-life. So we are going to represent it as T half. Half-life is represented by T 1 by 2. So T half. Rearrange the equation. T half is ln2 over K. What's the value of ln2? Check in your calculator. ln, not logarithm. Natural logarithm. What's the value? 0.693 over K. This equation will be given to you in the exam. Now I have a few questions based on this equation. You remember the half-life of zero order kinetics? You remember the equation? Was the initial concentration over 2K? Now this is first order. T half, T half is 0.693 over K. Let's see the difference. In the first order kinetics, is this half-life dependent on the T half is your 0.693 over K and initial concentration is not the part of the equation. So this half-life is constant always. You can start your reaction with 100 molar, 200 molar, 1 kilogram, 2 kilogram, 1 quintal, 20 quintals, whatever is the amount. Very large, very small, in 10 raised to the minus 6 molar, very, very small. Half-life will remain constant, will not change. And it is very important to note here that all the radioactive reactions, the radioactive reactions, nuclear reactions, they define half-life. Radioactivity, radioactive nuclear reactions is not the part of AP chemistry, but earlier it was. Now we are not teaching it. But all radioactive reactions, the nuclear reactions, where the nuclear decay is taking place, the radioactive reactions are all, it's important, are of first order kinetics. That's why they have fixed half-lives. Uranium has a constant fixed half-life. Uranium, plutonium, francium, all these are radioactive. Anil is writing, I think, period 7, he's right. In period 7, all elements are radioactive. In fact, after uranium, if you go to that F block, uh, the 5F series, in the 5F series, after uranium, all the elements, they are formed by the disintegration of uranium. They all are radioactive. And all these decays, these are called as radioactive reactions or decays. The nucleus is undergoing a decay, breakdown. They all are of first order kinetics. So their half-lives are fixed, fixed half-lives, right? We are good with this? Now, if I ask you to make a graph of concentration of A naught versus T half for first order kinetics, how the graph will go? First order, like this, isn't it? Yes, Anil, good. But how the graph will go here in zero order? This represents a straight line. This is your T half, and this is the concentration of A. So when the concentration of A is zero, what is half-life? Zero. It will go like this, isn't it? Y-intercept is zero here. Make yourself expert in looking at the equations. Big physicist, chemist, if you have this opportunity of watching some good movies nowadays, people are making really very good movies on scientists, Oppenheimer. So everything they are doing on the paper mathematically. They were trying to prove their theories mathematically. Mathematics plays a very important role in understanding of the science also. And most of the, like there is one equation, de Broglie's equation. De Broglie was not a scientist. Scientist in the sense that he was not something physicist or chemist. He was a mathematician. His equation is very important for us also, for chemistry, for physics, very, very important. So mathematics plays a very important role in understanding or in proving your point. Bohr's theory. Bohr's theory was what? He math On the paper, he did everything. He made the structure of atom. Then he proved it mathematically. You have to prove your theories, right? Only then that theory will be accepted. So mathematically, they have to prove it. And then they are using all big mathematics. You know, Oppenheimer, when I was in the college, way back, I think more than 30 years now. So we were doing quantum chemistry. I was in my final year of the graduation. And then there was a Oppenheimer operator in the book. And I used to find it very difficult. So operator was named after him, Oppenheimer operator. So when I saw this movie, at that time I used to be very scared of that operator. Okay. So all this is mathematics also. Understand? And you can see in the movie, most of the time they are proving everything mathematically and then they are doing experiment. So this is your half-life of the first order kinetics. In graph, should y naught be a naught? I'm taking this equation, Anil. This is y, this is x, right? So I just answered one question asked by Anil. Okay, so now let's go for the same story. The story I said here for the first order, for the zero order. The same story I'm going to repeat for second order. We can do it faster, right? I'm not going to show you the integration because that's not the part of your learning. So let's move faster. We are working with second order. All of you, please keep helping me. Second order. It's a repetitive story going on. Reaction A to B. Rate is minus delta A over delta T, which is also equal to K times concentration of A is second order raised to power 2. Rearrange and integrate 0 to T, 0 to T. Calculus. Then you get an integrated rate law 1 over AT. T means time. Concentration of A at any time interval during the experiment minus 1 over A naught is K times T. This is plus this time. Mathematically, we can prove it, right? This is the integrated rate law of the second order kinetics. Is it clear, children? Integrated rate law. We are good? Now, I'm going to rearrange it in the straight line format. So, concentration of A at time t is kT plus 1 over concentration of A naught. Now tell me the graph. What is here on this axis? Look at this equation. It represents a straight line equation, right? So what is here on this axis? Is 1 over AT. What is here? Time. Good. And the line will go with the positive slope. The slope of the line is K. What is this point? Y-intercept 1 over A naught. First order, zero order, second order integrated rate laws is the part of your learning. Means there will be questions based on that. What's the half-life? Let's work out the half-life. Half-life for second order kinetics. So what you have to do? You have to replace your concentration of A after half-life as A naught over 2 in this equation. Just do that and you'll get half-life. AT, oh sorry, it's 1 over this one, 1 over concentration of A. So it is 1 over A naught over 2. I replace this concentration of A at time t by A naught over 2 is equal to K. This t is time, children. T is t half now plus A naught. Rearrange the equation and you will get t half as 1 over A naught K. Rearrange, do the mathematics on your own. Otherwise, no one is asking again. But it's fun how these equations are formed. They are not tough. Now, this is the equation. Answer my question. If A naught is more, T half-life is less. How the graph will go if I take T half here and A naught here? It will go down, right? So that's the story of the second order kinetics. Can you see how they are resembling? This equation will be given to you, children, this one, which you can rearrange like this. Half-life of the first order kinetics will be given to you. But half-life of other reactions, other orders are not tough. We are not going to talk about third, fourth, fifth. That you will come to know when I'm going to discuss collision theory. That will be the last topic of this unit. So children, there are total 9 units. We have already done 4 and the 5th unit is done. By the next class, it will be over. Now your units will run faster and they are more important and they are easy also, not tough. The way unit 4 concentration, there is that, so many things are there. Unit 3 is so much lengthy because I have to teach you all the physical properties, separation, making of the solutions, ideal gases, real gases. Unit 3 is also very important. But now the syllabus will go very fast. Please do not miss classes. And this is the most important part of your AP testing. Rest are the part, they are making the basics. They are also important. It's not that they are not important, but this is the major part. And this part is not tough at all. So I will be going fast because topics are less. So we are done with the integrated rate laws. Now answer my question. If there is a graph of A, concentration of A at any time t versus t is a straight line, what is the order? Straight line. What is the order, children? 0. If ln at versus t is a straight line, what's the order? What's the order? First. This you should know now. And if 1 over at versus t is a straight line, then what's the order? Second. And we worked with the half-lives also, right? So I'm taking you now on the questions. So this was the last question of the last class. We were doing this question in the last class. See, all these things I have discussed with you. Half-life also. Can you see? So this is the straight line. This one. So I'm going to run it very fast because these things we have done on the whiteboard. I would have done here also, but so many things are written and you'll find it difficult to understand. I hope you have understood integrated rate laws, right? This is integrated. A versus T, zero order. Remember this, it's very important. Okay, first order kinetics, rate law is this. Half-life is this. Here is the rate law. This one. Integrated rate law, which we have done. Second order kinetics, integrated rate law, and half-life is this, right? All these things we have done. Ready for this question? This is a question, children. Now all eyes and brain should be engaged in doing this question. All of you. A naught is this. Initial concentration. A naught not means when the time is zero. Concentration versus time data collected. It's an experiment. So they collected the data. What's the rate law, children? What is the rate law? Is this the answer, Aditi Ajumi? Rate law, it is first order kinetics. How did I know that is first order kinetics? Because they have given me here. Hint. ln A versus T is a straight line. So it means the rate law is rate equals to K times, rate laws are always in terms of the reactant, concentration of A raised to power 1. That's the rate law. What's the integrated rate law? That you can pick up from the formula sheet also. So ln AT is minus KT plus ln A naught. That's the integrated rate law. What's the value of rate constant? So the graph is ln AT versus T with a negative slope using this equation. So what's the slope? Slope is minus K. But the slope is given to you here, see? So what's the value of K? We are doing A part. What's the value of K? Minus, 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 there is minus here and minus here. So plus 2.97 times 10 raised to a minus 2 per minute. Units are minute, take care. Time here is in minutes. Okay, B part. It's a first order kinetics. So what's the half-life of first order kinetics? The equation will be given to you. You have to pick up the equation. They will not write anything after the equation. They will not tell you this equation represents the half-life. That you have to decide yourself. What will be the units of this T half? Units. What will be the units, children? Minutes, not seconds. Okay, minutes. Because K is given to me per minute. Per minute, you remember? Per second, per minute is the unit of rate constant for first order. We did this in the last class. B part is done. C part. How much time is required. So they're asking T. For the concentration of A to decrease up to this. So what is the concentration at time T? 2.50 times 10 raised to minus 3 molar, right? And what is the initial concentration? It's given. See here. This is initial. 2.00 times 10 raised to minus 2 molar. Correct? Then they're asking T. Do you have K? Yes, it's given here. 2.97 times 10 raised to minus 2. Now this is just mathematics. Use this equation, this one. Integrated rate law, ln AT. You can use any format, like you can use this one, ln of A naught over AT. Easy to use, AT. Mathematically, you remember I have shown you different formats. Practice them. Use this format. It's easy right now because you want to calculate T. So what is T? T is 1 over K. See, I'm just making you familiar with different formats. If you're not comfortable, don't worry. Plug in the values here. Plug in AT, plug in K, plug in A naught, solve it. Your graphing calculators are permitted. So you need not to practice so many equations. You can just plug in the values here. And then you plug in the values and you will get your answer for T. You know K, you know A naught, you know AT, you get the T. What will be the units of T? Units of T, children? Minutes. Take care of that every time. Units are very important. So you can plug in values like this, 2.97 times 10 raised to minus 2 ln A naught is 2 point, answer should be in three significant figures. Minus 2 divided by 2.50 times 10 raised to minus 3. This one. Solve it. So mathematics I'm leaving. Are you okay? So these type of questions can be there in the free response or in MCQs, multiple choice. Ready for next? Okay. Do this one. I hope all of you are reading the question. When you are reading the question, just check this line and answer this. Reactant is this. So what's the rate law? First order, zero order, or second order? It is zero order. Remember, concentration of AT versus T. A straight line means zero order. ln AT versus T is first order. 1 over AT versus T. Memorize it, practice it. Second order. We have understood all the equations, we have understood all the mathematics. So keep practicing it. So what's the rate law here? Zero order. So rate equals to, I'm writing the rate law. Rate equals to K times concentration of C2H5OH raised to power 0, which is nothing but K. That's the rate law. Anil, if you missed typing K, then you have not written anything, right? This is the rate law, children. And what's the integrated rate law? So that will be given to you, but you need to identify AT minus KT plus A naught. That's the integrated rate law. What's the value of rate constant? K. You know, the graph is concentration of AT versus time with a negative slope, and the slope of the line is minus K, and that slope is given to you. So it is 4.00 times 10 raised to power minus 3 molar per second. Units are different. It's a zero order kinetics. Units are different. Molar can be written as moles per liter per second. That's what they are writing. Molar means moles per liter, molarity. We know molarity very well now, right? So A part is done. Can we do the B part? How much time? So use this equation for all this to decompose, all of it getting decomposed. So what's the concentration of AT? If all of it is decomposing, zero. So 0 is minus KT, T they are asking, plus A naught. A naught is this 1.25 times 10 raised to a minus 2. Plug in K, which you know this. So rearrange the equation. Isn't it 1.25 times 10 raised to power minus 2 divided by 4.00 times 10 raised to power minus 3? Is this answer? Is this the answer? Can you check mathematically? And the units? Seconds. Because you're working with seconds. See, the rate constant is in seconds. That's why. Are we getting this answer, children? So just mathematically plug in the values. All of you are getting this answer? Okay, very good. Move on. So children, I'm not calling your names today. The reason is we have to do plenty of things. So please participate yourself without calling the names. Check this question. This is another question. Same story every time. Read the question. The rate constant is given with units. They are not telling me whether, oh, they have already said, okay, fine. It's very simple, it's zero order. They've already said in the question, zero. K given, K is given. A naught is given. Integrated rate law is A naught, AT minus A naught is minus KT. Or you can write it in the other format also. That's the integrated. I'm interested in this question. I think there were other questions also, but they were very repetitive. So I found only these questions new. So I picked up this only. Question is, what is the concentration of B after this much time? B is the product. They're asking for B, not for A. So how I'm going to work out the answer? Because my equation is in terms of reactant. Don't you think that the amount of A which is converted, you started with A naught, you are left with AT. This difference, the amount of A which has reacted, is actually B. This is how the equation is. Minus delta A over delta T is plus delta B over delta T. Whatever amount, this is 1:1, 1:1. Whatever amount of A has reacted, that is B. And how much amount of A has reacted? So that is A naught minus AT. So do you know how much A naught is? So I'm going to calculate AT. If I know this, I can calculate this difference. So A concentration at time T is minus this value they have given me, 1.0 times 10 raised to the power minus 3 is equal to K they have given me. K is how much? This value, right? 5.0 times 10 raised to the power minus 2. Time they have given me, time, see, seconds. Take care of the units. 10 raised to the power minus 3. So what is 80? If you do this mathematics, it is minus 25 times 10 raised to the power minus 5. This minus will become plus. Can you calculate this 80 now from here? Use your calculator. How much 80? Mhm. I'm not using my calculator, so I'm just doing without calculator. You have to check my answer later on. So it is 2.5 times 10 raised to power minus 4 plus 10 raised to power minus 3. I can take out 10 raised to power minus 3 common. So it is 1 minus 0.25, 0.25, 1 minus 0.25. That means 0.75 times 10 raised to minus 3, 7.5 10 raised to minus 4 molar. That's the value of 80. Are you getting this, children? Okay, good. You need not to do all these mathematics. Don't worry. You can use calculator. Calculators are permitted. I'm slightly lazy in using calculators. Okay, good. We know 80. Now, but this 80 is not, this is the amount left. How much was the initial amount? This much. How much is left? This much. How much is used? So the difference A naught initial minus this AT is the concentration of B which is formed. How much is this? 1.0 times 10 raised to minus 3 minus 7 point, you can write it like this, 0.75 times 10 raised to minus 3. If you subtract it, you will get 0.25 times 10 raised to minus 3, which is the concentration of B, which is formed at that time, T, molar, which you can rearrange in scientific manner. Put it in scientific manner. Molar. See, that's the answer. Children, are you getting this? Yeah, rate of disappearance of A is also the same. So when the time is given and the initial concentration is given and the concentration of A left unused, you calculate it, then take the difference. That is the amount which has converted into B. The ratio is 1:1. So whatever amount of A is converted into B is used up, exactly same amount of B is formed. 1:1 ratio, children. Are we getting this equation, this method? This is very interesting. Here they are asking the product, not the reactant. So you have to use your that understanding that how much has reacted, how much has disappeared. So exactly same amount will appear. So you just calculated the amount disappeared, and from there you worked out the amount appeared in the same time interval. Moving on, children. Yeah, this is very interesting question, very simple. First order reaction. Who is going to give me the integrated rate law for the first order? But the very first question, that why are you using integrated rate law? What is the reason? Why am I using integrated rate laws? The reason is because in every question, they have given you initial. They have given you initial, right? And they are just talking how much is left. They have given you the rate constant values. They are talking about time. In the integrated rate laws, time is very important. You integrated the equation from 0 to t. But in this rate law, k times concentration of A, this rate law, time is not there. In this equation, where is time? So when you see your data has initial, final, time, rate constant, it means the question is of integrated rate law. Like here, time is given. They're asking half-life, integrated rate law. They have said first order. So what can I say about initial amount? Can I say initial 100? Because they are talking in percent. Then how much is left after this time? Can I say 25? 75 is used up. 75 is used up. Then I can use this equation ln 80 minus ln A naught is minus kt. What is 80? 100. What is A naught? 25. K I want to know. Time 320 seconds. Solve it. You can use this mathematics. 100 over 25 is minus k times 320. How much is this, children? ln 100 over 25? Oh, I think I did wrong. I was just thinking why I'm getting minus. 80 is 75. 80 is 25. 25. This 80 is 25. This is 100. So this is 25 over 100. Sorry. Use your calculator and give me the value of k. All of you, please get the value of k. Now this k will be positive because this is minus. This answer is also minus. This number is less than 1. Natural logarithm or logarithm of less than 1 is always a negative number. Aisha, what is the value of k? And give the units. K is saying, Anil is saying k is 230.83. Is it right? Units, Anil? Don't put the value of k without units. I'm not getting this answer, children. No? Yeah. Anil, check your mathematics. So answer which I'm getting, and if I take care of the sig fig, I'll go up to 3. So I'm getting 4.33 times 10 raised to power. Okay, this less light here. 10 raised to minus 3, I think. Units, seconds, so it is per second. Per second, dear. per second. Are we clear about it? But the question is why I'm calculating K. They are not asking K. But this is first order and they're asking half-life. We know that T half is 0.693 over K. That's why I'm calculating it first. I need this K for calculating T half. You just plug in the value. Can you work out the half-life of this first order kinetics? Half-life. Get the half-life, children. And you have to give me the answer with units up to correct significant figures. You're going to decide significant figures from the values which are given here. This is 3, this is 3, that's why K is also 3. So this one is going to decide the sig fig. How much? 159? I'm getting 160. I'm getting 160. Is it right, children? Anil, your equation is not right. The equation which you are giving me is for zero order, right? Half-life equation. Half-life equation for first order is this. Remember, it does not depend on the initial concentration. It does not depend on the initial concentration. So what is the half-life for the first? What is the value of half-life? First half-life, 160 seconds. What is the value of second half-life? 160 seconds. Third, 160 seconds. Because this is constant for this particular reaction. Because it does not depend on initial concentration. So half-life is not changing. Right? Half-life will change only for zero order and second order. But for first order, it is same. So we are good with this? Okay, let me tell you what's the meaning of this, that why it is not changing. Let's say you started with 100. What's the value after first half-life? What is the amount left after first half-life? 50. What is the amount left after second half-life? Second, first, second. That's the meaning of this first and second. 25. What is the amount left after third half-life? 12.5. What is the amount left after fourth half-life? Fourth, 6.25. What is the amount left after fifth half-life? Yes. Again divide by 2. 3.125 and keep going on. But if you see in the first order kinetics, this is initial for the first half-life. But for the second half-life, this is initial. For the third half-life, this is initial. For the fourth half-life, this is initial. For the fifth, this is initial. For the sixth, this is initial. So initial is changing continuously for the first order, for the second order, for the zero order, right? But for the first order kinetics, this half-life, if it is 160 second here, it's going to be 160 here. Is going to be 160 here, 160, because it does not depend on the initial concentration. Initial concentrations are changing continuously. You see, they are changing. They are changing. But this change in initial concentration will not change the value of your half-life, because in the equation here, the half-life does not depend on the initial concentration. So it is constant. Very important concept, children. That is the reason all radioactive reactions, they have exactly same half-lives. Yeah, their half-lives are constant. You take 1 quintal of your uranium, or you take 1 milligram of uranium, half-life is same. So I'm going to share some questions. One more question I want to do with you people regarding this weight loss. Just give me 1 second. I'm trying to share it. I was expecting this question here in the presentation, but it's not there. It's a good question, important question. So, children, I'm trying to give you exposure of all types of questions. So please work hard. Try to get good marks in the school exams. For the school exams, I've already told you that you can use my forum. You can put your questions there. Question 45. See this question. This one. Very easy question. Answer it, children. What's the order of the reaction with respect to A? This is the reaction. These are the graphs. A versus T. ln A versus T. 1 over A versus T is straight line. Any one of you answering? Can you see the question? You can see the question, am I right? This is 0. This is first. This is second. Which one is the straight line? This one, right? So what's the order of this reaction? Second order. So rate is equal to K times concentration of A raised to power 2. That's the rate law, children. Straight line represents the order, right? Here the straight line is of 1 over A versus T. So from this graph, I identified, oh, this is second order kinetics because this graph is straight line. Is it okay? But there is very important question. What is the initial concentration of A? They're asking A naught. You know the rate law. 1 over AT is minus 1 over A naught is KT. You can rearrange it. KT plus 1 over A naught. So they're asking me that give the answer for this A naught, initial concentration, from this graph. Nothing else is there. Nothing else is there. They have not given me K value. They are not asking any T or something. Nothing is given. This graph is given and they're asking what's the value of A naught. So extend this line. What is this 1 over A naught? Isn't it y-intercept B? Let's say this point is 10, right? So what's the value of 1 over A naught? Not A naught, 1 over A naught. This y-intercept, 10. So what is A naught? What is A naught, children? 0.1 molar. This we calculated from the graph because we know that the y-intercept is 1 over A naught. So when you use a scale, then you are landing here in the center of 20 and 10. So that is 20 and 0, in the center of 20 and 0. That is 10. So 1 over A naught is 10. A naught is 1 over 10. That is 0.1 molar. Is it okay? It's a good question. Okay, children. So coming back on my this presentation, we are here. So we have understood the average rates, instantaneous rates, rate laws, and then integrated rate laws. Rate laws, integrated rate laws. You need experimental data for that. First, we perform the experiment. If you see, making of the graphs will not be there in the exam. See here this question 42, 43. What is this? This is experimental data. Experimental data. They have given you the time, the change in concentration. This is your A naught, initial concentration when the, oh, this is not A naught. Okay, they are starting at this time. So you can take it as A naught. And these are ATs at different interval of time. So all these are experimental data, experimental. So for the integrated rate laws, for normal rate laws, we need experimental data. Then the next important thing is again rate laws. But this time you are going to work out rate laws. You are working with different types of rate laws, average rates, instantaneous rates, rate law from the experimental data, rate laws from the integrated experimental data. So you are working with the rate laws. Your aim is what is the rate law? What is the rate law? This is another method to work out the rate law. It is based on mechanisms, mechanisms of the reaction. Okay, you can see the document, am I right? You can see it? Okay. These are called as mechanisms. In the mechanisms, we have every step clearly mentioned how the reaction is taking place, mechanism. Like, for example, this is you, your house, and this is your school. The path which you are going to follow to reach the school, like this. Exactly, we have the path of the reactions, that how the reactant is converted into product by different paths, and understanding of every path is the mechanism. So you will divide the reaction into different steps, and then those different steps are called as elementary steps. They cannot be further divided. This is an elementary step. It cannot be further divided. So I'll explain you this in the next class. And come and join me at the right time, because now what is left of this unit 5 is real fun. You will definitely going to like it, and is important also. No mathematics here now. Okay. So see you in the next class, children. If you have any questions, you can stay back.